Hi, we're going to talk about area and perimeter and some of the other topics that are associated with area, and this is of course under our theme of geometry. So first of all, when we talk about area, we need to think of area as covering versus perimeter as surrounding. Remember that area is multiplicative in nature because of the structure of the rectangles that can be broken into squares. And so here's an example. Here I have 4 rows of 3 squares in each row. So by property of multiplication, I know that what I have here is 4 groups of 3, or 4 times 3 square units. And then, so of course, remember that area is measured in square units, where perimeter is measured in linear units. And perimeter, of course, is just the distance around when counting the side lengths. Of course, you have to be careful when you're counting the side lengths that you're not counting the actual square units as you're counting around, but that you're counting the length of the side. So in this case, we would want to count 3 here plus 4, and then double that, another 3 and another 4 to get our perimeter. A common misconception that students often make is they try to count the perimeter this way, that I have it kind of marked up here, and what that does is that leads them to not just an incorrect answer, but a misconception in what perimeter is. If they're counting the square units here, they're missing the idea that perimeter is measured in linear units. Okay, so now let's talk about the moving and additivity principles. We talked about these a lot as ways to kind of validate our area formulas. Sorry about that. Okay, so the moving and additivity principles. First of all, this basically just means moving, and that's if we move a shape, its area doesn't change. And then the additivity portion of that principle, that if you combine shape parts, so if you take a shape and then you combine the parts, in other words, cut apart that shape and then combine the parts, the area stays the same as the original shape. So here's one example. If you start with a rectangle that has an area of 20 square units, and then you cut a portion of that rectangle out and you place it here on the end, so that you haven't removed any total parts, you've just moved this portion to the outside here, you still have an area of 20 square units, according to the moving and additivity principle. We also talked about using this principle to show the area of a triangle in 3 different ways. So I'm going to talk about all 3 of those ways here. So in this triangle, if we're looking at half base times height as our area formula, then we can validate that by showing that a triangle is half of the base times height when looked at as a rectangle. So the entire rectangle would have an area of base times height, and then of course the triangle is half of that. So that shows half of the base times height. In this example, we take the same triangle. This time we're cutting the height in half. So we're taking half of the height, and then we're moving this piece, because we cut right there, and then we're moving that piece to right here. So we are able to form a rectangle. So in other words, we're using the formula of a rectangle to validate the area formula of a triangle. So again, we're able to take half the height times the base to get the area of the triangle, which will stay the same, again, because of what we know about the moving and additivity principle. We're going to do that one more time with the triangle. This time we're going to cut the base in half and multiply that by the height. So again, we end up with a rectangle with the same area as our original triangle. Same thing applies when we talk about parallelograms. So in this parallelogram, we are looking at it as an entire rectangle to find the area. And we know to find the area of the rectangle, we would take base times height. So in this case, and that's going to work for a parallelogram base times height, but it's a little bit harder to see. So this way we can see it, because what we're going to do is we're going to take the area of the rectangle as this entire base, a plus b, times that height. And then if we use the distributive property, then h times the quantity a plus b is the same as ah plus bh. And then if we take away our ah, which is our 2 triangles here, this triangle and this triangle, and we put those together, we get a square or rectangle that has the area AH. So if we take away that AH, we're left, of course, with BH, which we know is the area formula for a parallelogram. So once again, we're able to validate the area formula for a parallelogram with the area formula of a rectangle. Now let's talk about circles. Circles are really fun to talk about because there's lots of different ways for us to look at circles in maybe new and interesting ways that we haven't seen before. So first of all, with circles, we know that we're dealing with pi, and pi seems to still be a little bit of a mysterious number. Of course, this is a Greek symbol, pi, but pi is simply a ratio, and it's a ratio of the circumference and the diameter. So if you take the circumference of any circle and divide it by the diameter, you're going to find that it's pi, approximately 3.14159. There's lots of different ways for us to validate the area formula of a circle. One of the ways that we talked about is by taking pieces of the circle and basically cutting them like they're pie pieces and then putting them together. So that's what we did here. We just took a circle and we cut it into pieces of a pie. So it'd be like taking the circle and then just cutting it like you would a pizza or a pie. And then we took those pieces and we merged them together. And you can see that when we do that, we get sort of a rectangle. The thing that we have to remember when we do that is that this distance from here to the center of the circle is the radius, and it's always going to be the radius. And that this distance on top is half the circumference, because the other half, of course, is down here, and that would have made our full circle. What we can do at this point then is we can take our pie pieces and cut them in half so that they're even smaller and they fit together even tighter, and that's what this is supposed to be showing you. The radius stays constant, stays the same, and same with this distance on top, which is half the circumference. And what I'm trying to show here is that this sort of looking like a rectangle ends up looking more like a rectangle here. If you were to continue this process and cut your pie pieces into even smaller and smaller chunks, you would eventually get what looks like a rectangle. Again, with your radius here and your half circumference here. Now let's talk about how that can help us find the area formula for a circle. So we know how to find the area of a rectangle. That's the first thing that we talked about, which is length times width. But in this case, our length is half the circumference and our width is the radius. So we're going to take that information and we're just going to work with it until we get to the area formula for a circle. Remember, the circumference can be thought of, the circumference divided by the diameter is pi. So circumference then would be pi times diameter. So half the circumference is also written as half pi times diameter. And then, of course, times the width, which is the radius. Now we're going to rewrite the diameter in terms of radius. So half the pi times 2r, because a diameter is just simply 2 radius, or radii, times the radius. And then, of course, we're left with pi times radius squared, or pi r squared. We also looked at how you could take a roll of, we used gum tape in class, but a roll like this, and show or validate the area of a circle using the triangle formula. So that's what we did here. So we cut the roll of gum tape from the outside, from the outer circumference to the inside center. So basically what we're cutting is the radius. And then we just simply unraveled it, and so of course we end up with longer pieces on the outside and then shorter pieces in the middle, and we ended up with a triangle. So it's important to remember when we end up with this triangle what the dimensions are. Of course, that long outer piece on the outside is the circumference, and the distance from the very center to the outside is the radius. So now what we're going to do is we're going to apply the triangle formula and see if we can validate the area of a circle formula. So we know to find the area of a triangle, we take half base times height. In this case, your base is your circumference, so we're taking half times the circumference times the height, which is r. We're going to rewrite that circumference, just like we did over here, as pi, 2 pi r. So half 2 pi r times radius ends up with being pi times radius squared. Okay, and then lastly, I just want to talk about the Pythagorean theorem. And we're just going to talk about this briefly. First of all, I just want us to remember that the Pythagorean theorem is a relationship, and that's what it's all about. This is not just about numbers. It's actually a relationship among the sides of a right triangle, and only a right triangle. In fact, the Pythagorean theorem is often used to determine if a triangle is a true right triangle or not. So this isn't just about numbers that you plug into some random formula. It's all about this relationship between sides. But what we can do with the Pythagorean theorem is we can remember that what this means is that if you have the area of one side plus the area of the other side, so the square of this side plus the square of this side, that's going to equal, the sum of those two will equal the square area on the hypotenuse side, or the third side. So we're going to prove the Pythagorean theorem. This is maybe one of the more famous proofs of the Pythagorean theorem, using the moving and additivity principle, since that is the principle that we talked about a lot throughout chapter 12. So what we have here is we have a bunch of parts. So this part is called a squared. This squares called b squares, and that's because, of course, this side length is b and this side length is b, whereas this one is a and this is a. And then we have this side length over here, which is c, and this is c. They all correspond to the triangle side lengths of a, b, and c. And you'll notice that this side of the square that is a is also that side of the triangle that is a. This side of the square that is b is also that side of the square that is b. This side of the square, or triangle, that is c is also that side of the square that is c. So what we do if we have all these pieces, we can actually form two identical size squares, and they fill those squares perfectly. And so how we can use this to prove the Pythagorean theorem is by adding up our parts and see what we have on each side or in each square. So over here we have an a squared and we have a b squared, and we have 4 of these triangles, and I'm naming these triangles ab divided by 2 because I know to find the area of the triangle I take the base times the height divided by 2. So I have 4 of those. I have 4 ab over 2's. And then over here I have c squared, plus I have, again, 4 ab over 2's. So what I'm going to do is I'm simply going to move, that's using the moving and additivity principle, I'm going to move the 4 triangles from here, and I'm going to remove the 4 triangles from here. And the moving and additivity principle states that since we started with identical size areas of the whole square, then removing the same size parts should leave us with the same area at the end. So in other words, if I remove 4 triangles over here that are the same size as the 4 triangles that I'm going to remove over here, then we should be left with the same area on the left as we have on the right. And algebraically, I'm showing that that happens, and we're left with a squared plus b squared over here, which equals the area over here, c squared. Okay, I hope that helps. Thanks for listening.